Okay. All right. So let's start the chapter 5. So last time we talked about the chapter 4. We talked about the cycloalkanes and how you're gonna do chair conformation and all the other related problems to it. So the chapter 5, we're gonna do stereochemistry. Okay. So we're gonna learn about some priority centers and tetrahedral structure. What we're gonna do here is we try to find some stereochemistry of certain compounds and how and when we can apply this knowledge in organic chemistry. So I hope you guys remember we did the isomers, we can say isomerism. It's in mainly two categories here. So last time we talked about the structural isomers. Or you could say the constitutional isomers that share the same chemical formula. But there's no same bondings, okay, between carbons and other groups. Okay? So then we can have this isomers. So literally means they are same in the chemical formula, but just structure different when they do not share the same bonding among the carbons in the compound. If that is the case, what if we have they also share the same chemical formula, okay. But also the same bondings too. Then is the same still? No. So even though they share the same chemical formula, same bondings, in a certain case, it's still not the same compounds. In here, we call this stereoisomers. So they share the same chemical bondings and formula, but still different compounds. Then these two different compounds to each other, the relation between these two different compounds are stereoisomers to each other. Make sense, right? Okay. So if that is the case, let's try to look at this one. So in your stereoisomers, okay, mainly we have two. In stereoisomers, we have geometrical isomers, which we'll do when we cover the alkene. Okay, so don't worry about this one at the moment. Okay, just let's put it aside. There's two other, which is diastereomer isomers, which also do it later. But the one we're gonna do this chapter is what we call optical isomers. Or we also call this enantiomers, or you can say enantiomers. Either way you pronounce is fine. Most people in the States pronounce enantiomers, but other people in Europe, maybe they pronounce like enantiomers. Then just make sure that there's a meaning the same thing. Okay, just how you pronounce. Anyway, so we're gonna focus on this one today. Okay, so let's talk about this one and why it's so special. One of the things we're gonna discuss with the diastereoisomers will be this one. But today, let's focus on this topic in this chapter. Okay? So mainly in this chapter, besides the geometrical isomers, we're going to talk about the optical enantiomers and also diastereomers in this chapter. But today, let's do enantiomers first. Okay? Make sense, right? So the problem, the first question we can have for this chapter is, what is then chiral center? And why it's so important? Why we care about this one so much? Okay, so this is chiral. Chiral means it's like a hand from the Greek word. So the even though you and hands on the mirror image, then on the other side will be the right hand. So it can be this very look the same, but can be the same. Because the left and right hand is different. So anyway, let me show you the one example. So if you look at the carbon here, it has at max, how many single bonds it can have? 4, right? This is in the 4. So when it has 4 bondings, okay, got the carbon over here, and you try to put the mirror next to it. Okay, get the mirror here. And if this carbon should have a tetrahedral structure because it has the 4 bondings, right? And then when you try to put each group on this carbon, 4 different groups, on this same carbon here. So I'm gonna just put it like A, B, C, and D. Okay? Not the same. It's not AA, BB, it's like A, B, C, D. It's all different groups on this carbon here. And you try to draw the mirror image to this one. Okay? Okay. And then you just need to put the carbon at the center again. But this is the here. Okay. This is here. This will become here. Right? Makes sense, right? So mirror image here. So if you make a mirror image of this one by doing this, obviously they have a what? All same bond too. This carbon, BA, all different bonding, or I'm say all different group to this carbon bonding are the same on here and here, but it's just a mirror image to each other. So then, if you try to rotate it, to make it overlap to each other, but it's not the same. If you rotate it, there's still been the different, because this is a tetrahedral structure. So it cannot be the identical still. So if you have groups all different here, even though you rotate it to make it like overlap to each other, it's still not the same. Okay. So even though they are mirror image to each other, they cannot be the same. They cannot be the same compounds if they have 4 different groups on carbon. Okay. So if there is only 3, then it's the same. Can be the same, because this will be what? This will be triplanar. So you can just flip it. There should be overlap on the same angle right there. But if there are 4 different groups in tetrahedral structure, even though you make the mirror image out of that, they cannot be still the same compound. So we call those 2 enantiomers, because they are not the same compound. When they have 4 different groups on carbon. Makes sense, right? We good?
So are you saying that if there's only 3 that it can, or?
Oh yeah, if there's only 3, then if you flip it, it will be the same.
Okay, so it's just like that.
This will be triplanar. So it will be triplanar in the same plane. This one. Yeah. So, but if there is 4, they cannot be the same, even though it's mirror image to each other. So we call them enantiomers. Okay. So try to remember this one real quick. I'll give you a couple examples here. So let's try to do practical problems over here. So if you have this one, can try to have this one over here. Are going to have the groups on the 3 carbons in here, right? Then try to find the chirality center. So chirality center means the carbon that has 4 different groups. So you can try to find how many chirality center does this compound have, meaning how many carbons will have 4 different bond, 4 different groups on it. That's the same meaning. Okay? So if you look at this one over here, this carbon has, if you look at it closely, this carbon 1, 2, 3, and over there. So obviously this carbon cannot be chirality center because it has the 3 same hydrogen attached to it, right? So this is no good. Okay. Then this one, if you look at this one here, because of these 2, right? The same groups, right? So this is also cannot be a chirality center here. Okay. And here it has all different groups, but it has only 1, 2, 3. So like I said, it also cannot be chirality center. So in this case, there's no chirality center in this compound. Okay. But if you have this one, in this case, this carbon is, this carbon can be chirality center. Because this carbon, from this carbon view, it has sort of a 1 methyl group on it, right? CH3, and 1 hydrogen, 1 hydroxyl group, and 1 carboxyl group over here. So they are all different to each other on this carbon. So you can say, oh, this compound has a chirality center in this carbon, carbon number 2. Okay. Makes sense, right? Okay, perfect. So let's do one more. If you have a 5 bromo decane, so decane means 10, right? And you're gonna put the 10 carbons. Okay, 10 carbons over there. And then this is the bromo groups will be on the number 5 carbon. So let's try to do 1, 2, 5 over here. So I'm gonna put over here. Okay. So in this case, those carbons are in the terminal carbons cannot be chirality in the center because it has 3 hydrogens on here, right? So they cannot be. And the one in between, it also has a 2 hydrogen. So those are also cannot be a chirality center. But this one, this carbon here, right? If you look at this carbon here, it has a bromo group here. And you also see there will be implied hydrogen there, right? This has to be 4. And then if you look at this one and this one are different because on this carbon, it has 4 carbon groups attached to it. 1, 2, 3, and 4, right? And here it will be 1, 2, 3, 4, 5. So this is the 4 carbon group, 5 carbon groups. So meaning you have all different groups on this carbon as well, in this compound. Because there's 2 different R groups. We normally put the carbon groups attached to the chirality center or any carbon. We call this the R groups. You consider them like the RQ groups, which they're not in compound. But to this carbon, they're kind of as RQ groups because R groups. But these 2 are not the same, different R groups, but different R groups, hydrogen and bromine. So that makes this carbon is a chirality center. Okay.
So we want,
Mhm.
for Cairo, whatever, we want it to all be different. We
Mhm.
want, okay.
Perfect. Yes. That's exactly right. So if you have any carbon that attached to 4 different groups, that would be your chiral center. Perfect. Absolutely. Makes sense, right? So we did some practice. So this is also something you may see on the exam. I'll give you some compounds, and I try to find the chiral center, which you need to find the carbon that has 4 different groups on it. Okay. Makes sense, right? Yeah.
So
Mhm.
this was nonane and it was 4 on each side.
Mhm.
It would not be.
Right.
Okay.
Perfect. Perfect. If it was a 4, absolutely. It's still not a chiral.
Okay.
Perfect. Very great question. Okay. So can I move on?
Yes.
Because these two will be the same now. All right. So let's move on. So try to remember we talked about the chiral center. Okay. Just for the moment. Okay. And then we're gonna do. We're gonna talk about the optically active compounds. Okay. There is a reason why we're gonna do this. So just hold on to this one. I'll tell you why it's so important whenever we do the stereochemistry here. But this is just something that we need to know for the stereochemistry. So whenever you have some compound that is optically active means it interacts with the light. That's what it means. So optically means it's like there's a light involved interaction there with the compounds. So whenever it does with the light, they do something on the light, we can say it's optically active there. So the one characteristic you can do in optical property is when you shoot the light, okay. So you put the light to the compounds, okay, compounds over here, and then before you put the light on the compound, we're gonna do polarize the light. So we're gonna use the polarizer to polarize your light. So as you know, the light is what? Electromagnetic radiation, right? So that gives a lot of the wave property of the light comes into your the device. But whenever it does, light is combined with a lot of different oriented waves are all combined together initially. But when we have a really good polarizer, they're forced to be in only one direction wave, can pass through it. Okay? So in this case, when light pass through this polarizer, only this wave in this direction can go through. Makes sense, right? This is a polarizing the way. And then maybe this is started from here, like in this direction, and there's compound filled with some filled in the container, like some cylinder-like container. And then when this polarized light goes through the compound, it maybe changes the directions. So initially was this one, but maybe change it to maybe 20 degrees on this way. We can call this compound optically active. Some compounds doesn't do that, but some other compounds do rotate the polarized light, and then we can call them optically active. Okay. So. Mhm.
Why 20%? Is that just?
Oh, I'm sorry. It's 20 degree.
That's what I meant.
Oh, yeah.
Why 20 degree? Is that just a random number you gave?
Yeah, just the random number. So that's a really good question. This is why we have so all different compounds have a specific rotations. So we'll call this specific rotation. So they will show you the specific number for the degree of rotation when you pass through the same compounds over here. So this is what we're gonna do now. Okay. So here's a couple more things that I want you to know. That there are certain terms that you can explain when, where, like how they rotated, how much. So if it's rotated into clockwise, we can call this dextro rotatory. Dextro rotatory. Okay, if you go clockwise, right? This is the clock then. So then you can put the symbol as the plus sign in the parentheses. So when the polarized goes to the compounds, when it rotates, when it passes through the compounds, then we call this, if it's rotating to the clockwise, we can call this dextrorotatory, and then we can put the plus sign there. That means this compound will rotate the polarized right into the clockwise directions. Okay. Makes sense, right? It's rotated. Okay. So if it does it the other way, counterclockwise, right? Sometimes the light can be rotated in the counterclockwise. Okay. If in this way, that way we call them levo rotatory, and that is a minus sign. Okay. So this is only certain. So this is counterclockwise. So this is a certain terms that we use when we talk about the stereochemistry. I will tell you why soon. Hopefully today or Friday. But you just want to remember this one. So if they can rotate in a certain direction, a certain degree, you're actually going to have the optically active compounds. If it's rotating the polarized light into the clockwise, is dextrorotatory. Counterclockwise is levorotatory. Okay. So if that is the case, so for example, maybe some morphine or cocaine compound is the this one, and then I'll show this one. Sorry, and then sucrose actually turning on the clockwise. So those the different compounds who have a specific way to rotate the polarized right. Okay. So whenever you have a specific rotation in this symbol here, we just try to use a certain standard conditions. Meaning, think about it. If you have a compound here, if they do rotate the polarized right, that means if you have a more numbers of compound in this container, they rotate more, right? So the light, if the light goes through a lot more numbers of compound, it's optically active, right? It will rotate the light. So meaning, if you have a more numbers of the compound, the light just went through, you will be much higher number in degree rotated, right? So this is why we made a standard conditions. So we can use that number to find out, oh, this is might be this compound and this compound because they have a specific number for the specific rotation over here. So the condition is this one. Whenever you have a observed degree that rotated, certain degree is rotated, degree, and then it will be divided by its concentration and the path length. Because even though it's in the same path length, if it's a highly concentrated, that means you have a more numbered compound will get the light will get through, right? And also, if you have a long path length, and it also tells you you have a lot of numbers of compound, the light has to also go through as well. So we actually make this 2 at a certain standard condition. This is a 1 gram per mil, and which is the same as 1 gram per centimeter cube. Okay. And then, so this is concentration. This is concentration. The path length is set to 1 decimeter. That is equal to 10 centimeter. So if you have a certain compound at 1 gram per mole, 1 gram per mil, or 1 gram per centimeter cube, and only 10 centimeter or 1 decimeter path length in the container, that is your standard number.
We have to use decimeter for this?
Mm-hmm. Yeah, makes sense, right? Because if you don't have a standard condition for the concentration path length, it can be always different. It won't be you will not get the same number for the same compound. But if you can have one set conditions, you can measure the rotation. It should be always the same. So when you look at this number in this condition, you can tell what this compound is. And so kind of makes sense, right? Make sense? Okay. Okay. So let's do a bit of problem over here. Okay. So in your exam, we're gonna use this one, but this is just you only need to fill the numbers into this equation here. So you have observed the degree is rotated over concentration times path length in decimeter and gram per mil. So whenever I give you observed alpha, the degree rotated, was maybe I can say negative 16. Okay, negative 16, because it rotated counterclockwise, leave a rotatory compound. So you give in this much, but 16 degree, right to the left. Okay, and then concentration maybe was 2. Concentration was 2 gram per mil. Okay, condition was 2, and path length we use 20 centimeter. Okay, in this case, maybe I can ask you, what might be the specific rotation of this compound? Okay, and then only thing you really need to do is what? Here the numbers in here. Okay, so this will be negative 16, right? Negative 16, and this is 2. So we divide by the concentration because it has to be 1, but it's 2, so we divide by 2, so you can make the same condition, which is 1 gram per mil. And then path meter has to be in decimeter, but it's 20 centimeter, which is equal to 2. Perfect. So it'll be 2 decimeter over here. So that makes negative 4, which will become your specific rotation of that compound. It's
So
pretty
you said
easy. Yeah.
You would give us all of those?
Yeah, yes.
Test and then add?
Of course, I'll give you all the numbers other than what you're solving for.
Okay.
So sometimes I give you a number for this one already, and you can look for the concentration rate. So maybe let's try to do maybe positive 20, and then maybe you can say this is still 20 centimeter, and this is your x. So you're looking for concentration, and then I might give you is maybe 10. Okay, and then it's pretty much the same. You switch this one to 10, and switch this now plus 20, and this is your x. Yeah. There you go. So if you do this way, x is just 1, right? Because the 20, so the 10 equal to, and this one, so it'd be 1 times 2, it makes this. Well, you can flip it, so there will be but you know it's 1. Makes sense, right? It's not that, yeah. So there will be one exam that like on your exam like this. So either I'm going to ask you to solve for either concentration or the specific rotation. I never did the path length, so I will not do this, but these two usually. Or this one, maybe like these two. But no matter what it is, you can solve for anything if you have all the numbers anyway. So that's pretty much it.
Are there any units
Mhm.
besides degree on the -4 degrees?
The degree is okay. Yes. Because we're simply measuring how many degrees it rotates. Makes sense, right? All right. So can I move on? We good? Good. So, if that is the case, now we're gonna start finding out why we did this one. Okay, why we did this one. Okay, so we'll get there. I think I just look at the clock. I'll probably do it on Friday, not today. But please keep this in your mind and why we did this today. All right. So before we get to the actual point of doing this one with the stereochemistry, what we also need to do is Kani-Gold pre-log convention, or you can say rule. It just doesn't matter here, conventions or rule you can say. But Kani-Gold pre-log is just the last names of the three physicists. I think I actually the organic chemist. We just gonna use this one to find out if that chirality center has R or S configurations. Okay. This is I'm going to explain how and what this means. Don't worry about it. But this is what we're going to do now. So Kani-Gold pre-log convention means there's a certain way for us to find out what each chirality center has either R or S configuration. Let's do this together. Okay? So,
What's the last word?
oh, it's convention. So this word doesn't really matter. Some people call this Kani-Gold pre-log rule, or some people call this convention, but it doesn't really matter.
What's the third word? Pre-log?
Pre-log, P-R-E-L-O-G, pre-log. Okay. So this is just the last names of the organic chemists who made this system. Okay. So and the system is to find out if they have either R or S configuration here. And we're gonna talk about how we're gonna do this together. Okay. So let's try to look at the one compound here. Okay. Okay. So you have this compound, and I hope now you can see this is our chirality center. Okay, because it has a hydrogen, hydroxy groups, methyl groups. R groups, but here's another one over here. And then to use the Kani-Gold pre-log convention, you just need to prioritize each groups to like which one is the most prior, the which one is the least prior. We're gonna number them among those four. Okay, so we do that with the atomic number first. So whenever you do that, you look at the hydrogen over here, right? Which is if you look at the periodic table, it's the lowest possible atomic number. So obviously among four, this is the least prior groups always on anything. So this is our term here. And if you look at the oxygen here, that is on the second pair next to the carbon, right? So this is a higher in atomic number than carbon. So these two are the same carbon. So this is quite high in the atomic number, but this is higher than carbon. So this is obviously number one prior groups over here. Okay. And then if you have the problem is, what if we have a tie on same elements on these two? Okay. And then what you can do, you go further from there. So the methyl group will have 3 hydrogen on it, right? So we can put hydrogen, hydrogen, hydrogen on this carbon, And if you look at this one, it has 2 hydrogen and 1 carbon attached to it. So this is carbon, hydrogen, hydrogen. Okay. So in this way, they are taught in the first, but on the second part, this is slightly higher than hydrogen, 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 besides a carbon, hydrogen, hydrogen that attach to this carbon and this carbon. So among these two, this is slightly prior to the other, so it'll be 2 and 3. Okay. And then now we're done with the prioritizing the groups right in here. And only thing you have to do is you have this line and this line here, meaning obviously there's a tetrahedral structure. And the one this is heading this way, and the hydrogen one is heading this way on the back side of the board. So in this case, you try to look at, it's kind of hard to explain in 2D, but try to look this as a 3D. So this is coming, this hydroxy group coming front, right? And then the hydrogen group going back, right? And then you always look at your tetrahedral structure, try to imagine you grab this bond in your hand. And then look at those 3 other groups in front of your face. Okay, so that means this is already going back. So if you just look at it in this way, in this way, this is 1, 2, 3. So it's going this way, following 1, 2, 3. So whenever you're prioritizing the 4 groups, the least prior group, which is either hydrogen or any group that is the least prior group, should be heading back, even where you're looking at. So you're holding it that way, and then you just count how you can count the number 1, 2, 3, or 1, 2, 3. Okay. So in this case, it's going this way, right? This is the S configuration. When you go to like counterclockwise, in counting gold preload, it's S configuration. If it goes to clockwise, it's R configuration. So I hope that you may a little bit confuse later with the optical property of the compound and then RS configuration. They're only somewhat related, but they're not the same thing. So it means if there is some negative compound with optical property, it doesn't mean there will be either S or R specifically now, but they're only interchangeably related to each other. So I'll promise you, I'll do this again on Friday. But this is basically what we're gonna do with the Canning-Gold-Preload convention. Just prioritize the 4 groups and try to put the least priority group on the back and try to look at where the 1, 2, 3 goes in which way, either clockwise or counterclockwise. If we go to the counterclockwise, it's S configuration. If we go to clockwise, it's R configuration. That's all. That's the bottom line. I'll definitely do this again on Friday. Don't worry about it. Okay. But let's talk about this one a lot more on Friday. Okay?